Hello, let's do a paper 1B together. We're going to go through the paper 1B, which is the fun and exciting other part of the paper 1, some data questions. The paper 1, the way they're doing it now is a little chaotic and crazy because what happens is they're going to give you two booklets at once. Really, they're going to give you more than that because you also have like the data booklet and you also have a little answer sheet for your multiple choice questions. So you're going to have papers all over the place. You're going to be shuffling all kinds of stuff around your desk. It's going to be pretty annoying. So you need to go into the paper 1, especially with a game plan of how you want to tackle these things. My suggestion, I think the best way to do this, if I was doing this on a big stressful, I'm taking my first IB exam and it's physics, I would start with the paper 1B. I think the paper 1B is a good one to start with. This is, again, 20 marks is quite a lot, especially for SL people, honestly. And these are very doable. Like most of these are quite doable because it's all about stuff you've been doing for 2 years, which is like experimental questions about how uncertainty works, about interpreting data. There will be some definitely tricky ones, I'm sure, out of left field and stuff, but there's a lot of these that are quite doable. And remember, the paper 1A, the multiple choice, every one of those questions is worth just 1 mark. On the paper 1B, we're going to have questions that are worth like 2 or 3 marks for like doing math with uncertainty. So you can really like bang for your buck. Studying and practicing the paper 1B is maybe the best thing you can do if you're just like trying to focus on something, because you can really earn a lot here, like in proportion to how much. Versus if you try to master electromagnetic induction, there's like a few points you'll maybe get if you practice a lot. So practice the paper 1B, be feeling real confident about the paper 1B, and I would say start with the paper 1B. Time-wise, the paper 1B, again, it's 20 marks. You get 2 minutes per mark overall on the paper 1. So you would want to keep it to like 40 minutes or less for this guy because it's 20 marks. And then the paper 1A, which for HL is 40 marks, you would want to keep that to like 80 minutes or so. That'd be kind of the goal. So what I would say, a good strategy, if I were doing this, I would start with paper 1B and I would shoot for like 20 to 30 minutes. I wouldn't want to use up all my time. And I would find the stuff I can do easily-ish. Yeah, skim through and find the ones where you're like, yes, I remember how analog uncertainty works. Yes, I can draw a trend line. Pick up those marks because, again, you can pick up a lot of those 20 marks in the first 20 to 30 minutes, I bet you. And don't get too stuck on anything for super long. Don't spend like 5 or 10 minutes on a problem only worth 2 or 3 points. Right? You want to just like in your first pass, do as much as you can. Then I would go to the paper 1A where I might spend like an hour, I think would be good. And again, do the stuff that's like mostly easy. Don't spend 5 minutes trying to solve a crazy fraction problem. Find the stuff that's quick. Find the stuff that you recognize right away. Of the 40 questions, you might just do 10 of them on your first pass, truly. Like find the ones that go quickly first and then do another pass with the ones you like have an idea how to do, but might take a little while, and save the ones that you have no clue on until the end. All right, and then that puts you at about an hour and a half. Your last half hour or so is like cleanup. And this is where you decide how you want to kind of spend this time. Maybe you come back to the paper 1B where you're like, ooh, there was like a long math problem looking thing that maybe I can figure out, but it's going to take me a little time. I'll try to spend some time here. There were some multiple choice questions that looked like, again, they were going to be math intensive, or I forget, but I think I can maybe hunt through the data booklet and figure something out. So I'm going to try some of those, right? And then in your last 5 minutes or so, you make absolutely sure that you have put an answer for every single multiple choice question. Physics is hard. The IB tests are hard. but you've been working for 2 years, you've been studying for 2 years, don't leave anything on the table. Don't leave any multiple choice questions blank. Yeah, whatever you got left, just pick a letter. Don't even think about it. Don't be like, oh, I already have 10 C's. There can't be any more C's. If C is your favorite letter, put C for everything you didn't get to. Right? If A is your favorite letter, put A for everything you didn't get to. Make sure you put something down for all of those things. So anyway, that's the overall strategy I would encourage you to go for. Of course, you know yourself better than anybody. So if you find another strategy that you're going to be more comfortable and confident with, go for it. But I think this is a pretty good one. So again, the lesson is the paper 1B, you can get a lot of pretty easy marks pretty quickly. So that's a really good one to start with, and make sure you don't run out of time sweating on multiple choice questions. Okay, enough of that. Let's do some solving of a paper 1B. Okay, this is how they're going to go. They're going to give you some experiments. Sometimes they're like familiar experiments that you are, probably saw before in class. Sometimes, pretty often, they give you wacky, weird experiments that you've never really seen. That's on purpose. You're supposed to kind of think on your feet, read and understand what's going on here, and think about what's happening in the experiment. So this is a really good use of your reading time, by the way. You get those 5 minutes of reading time before you start actually doing the test, where you can't even pick up your pencil. Like reading through the experiments in the paper 1B is good to get yourself to start thinking about understanding what the heck is happening with this crazy experiment. I got like a conducting ball that's like penduluming back and forth between two metal plates, and it like gets charged by one plate and repelled from it, and then charged by the other plate and repelled from that. Oh boy, and so for a given potential difference, the ball bounces between the two plates with a constant period. Okay. They give me some data. I'm being careful to read every word when I go through this, because there's lots of little details in here that they're going to need me to catch and be looking for me to not catch, because they'll try to trick me. They bolded once because that's a not great move to do an experiment. I bet you they're going to ask us about that. V is provided by two identical power supplies connected in series. The potential difference of each of the power supplies is known with an uncertainty of 0.01 kilovolts. State the uncertainty in the potential difference V. Okay, a couple things here. State means you just say the answer, which in this case is just going to be a number. We're just going to say plus or minus however much, and that's it. Move on. Don't explain it. You just say the answer. No justification needed. And it's just 1 point, so we shouldn't spend much time. We got to catch that there's two power supplies. They're connected in series. I do need to know, you do need to know some physics for a lot of this stuff. Usually it's nothing too crazy. Like in this one, you got to know two power supplies in series, you add their voltages, right? So like this first one, the 3000 volts say level, these two maybe have like 1500 volts each. And they're both plus or minus 0.01. Sorry. Well, yeah, volts. I'm mixing my volts and kilovolts, which is not great. But they're both, 1.5 kilovolts with an uncertainty of 0.01 kilovolts. So I would add the voltages together. And I know how uncertainty works. That means I'm going to add the uncertainties together to get my total voltage. Right, like 1.5 plus or minus this much, add to 1.5 plus or minus this much. The uncertainty is just double the uncertainty of one power supply, because we got two connected together. That's 0.02. I do want to say the unit, which is kilovolts. Okay, there we go. That's it. Uncertainty for addition. Okay, then T is measured with an electronic stopwatch that measures to the nearest 0.1 seconds. That's my uncertainty of T. Describe how an uncertainty in the period of less than 0.1 seconds can be achieved using this stopwatch. They love this question, especially in this like paper 1B thing, because this is a very common experiment technique that you should feel pretty good about and have done, which is like anytime you're measuring something like this, you can't make this smaller. You cannot, like the time you measure, can't have an uncertainty less than that, because that's the uncertainty of the stopwatch. So how could you get a period that has less uncertainty than that? We'll measure more than one period. Yeah, measure multiple periods. It's a very, very common experiment trick. You measure multiple periods, it will make your uncertainty way better because you get to divide at the end. So like, okay, how about this one? Look at the 0.6. 0.6 seconds. This is 0.6 plus or minus 0.1. That's terrible. 1 out of 6 uncertainty? Come on, that's lame. What if you measured 10 periods here? Guess what? If you did 10 periods, you would expect to measure about 6.0 seconds, plus or minus still 0.1 seconds, right? Would be the time for like 10 periods. And so your period would be, it would have 10 times less uncertainty fraction-wise than you do if you measure just one. Yeah, so that's a very common trick. Measure multiple periods. That's basically the thing. So that's what they're going to want us to talk about. Okay, the way I'm doing this here, so to save you from just like watching me write on a tablet here, so we're just going to go to the mark scheme for a lot of these and look at what they want us to say. Okay, so for this first one, that's what they say. So 2 marks means I should like say what they should do and explain why, really. Okay, so describe how an uncertainty of t could be achieved. Well, you would measure the time for many bounces, and then you would divide the result by the number of bounces. And we could even maybe explain, because we don't get to see the mark scheme, right? So I might try to explain what that does in terms of making the uncertainty of your period smaller than the measured time. But that's it. Okay. Here's a graph of period versus voltage. The uncertainty in voltage is not plotted. Why is it unlikely that the relationship between T and V is linear? These are real simple. A lot of these where they ask you about like trend line stuff. All you have to say here, it's 1 point. Like, why is it not linear? Literally because you can't draw a straight line that goes through the error bars. It's all about talking about the error bars. The whole deal to see if like a fit is valid is, can you make your fit cross all the error bars? Well, no, there's no way you can draw a straight line that includes all of these, so not linear. And that's all they're going to want us to say. You can draw a straight line through the error bars. Make sure you say that, talk about that, think about that when you're drawing trend lines or answering questions like this about trend lines. A linear fit is valid if a straight line goes through the error bars. Calculate the largest fractional uncertainty in T for these data. Okay, so I want to be able to read error bars on the graph here. And they kind of already told me the uncertainty in T, I suppose, which is 0.1 as they measured it. So I want the biggest fractional uncertainty. The fractional uncertainty, remember, is like the absolute uncertainty over the value. So I'm thinking you're going to have the largest fractional uncertainty when you have the shortest period, right? For these guys here, the uncertainty of the value is a pretty big fraction of like the value itself. Up here, it's like 0.1 out of 1.4. That's not so bad. But what is it down here? What's our period down here? Well, looks to me, I'm reading the graph super carefully. I'm going to like use a ruler even if I'm not sure, and I want to make sure I'm like looking at the right line. But that's definitely 0.5 seconds. Okay, so fractional uncertainty, I just need to know what this means, is the uncertainty over the value, right? So 1 out of 5 is going to be 20%. Hey, look, that's 2 points right there. That's worth just as much as 2 whole multiple choice questions. Picture 2 of the hardest multiple choice questions you've seen. Would you rather spend 10 minutes trying to figure those out, or would you rather get these 2 points? Get those 2 points. All right, there we go. That's it. So you get a point just for identifying like this is the right time to pick. You like that you chose a 0.5 seconds time, and you get a point for getting the right answer. Okay, we keep going. The students suggest a theoretical relationship. This is usually how it goes. They like basically are going to give you weird data, a weird experiment, then they're going to linearize the data and ask you to like draw a trend line and do some stuff. Okay, so A is some constant, so they're guessing T is proportional to 1 over V, with A as like your constant of proportionality. The slope of this graph is what that's going to be. To verify the relationship, we plot T versus 1 over V. They're linearizing. Good job. Determine A by drawing the line of best fit. Okay, you're very likely going to have to draw a line of best fit on the paper 1B. Use a ruler. If you're not using a ruler, just go ahead and take your test booklet and crumple it up and throw it on the floor. because you're basically doing that. Use a ruler. You got to draw a nice straight line. You got to get an accurate slope as you can. So usually they give you error bars here, but remember the idea of a trend line, of a best fit line, is you're trying to draw a straight line that like kind of splits the difference between all your data points. Like officially you're trying to like have the same, you're missing like above just as much as you're missing below. So this is gonna be kind of tricky for me with this thing here. Okay, I got one I'm pretty happy with here. It's not always going to go through the origin, although that's a pretty good starting point, and that seemed to work pretty nicely here. Remember, there can be like systematic error and stuff, so don't assume it's going to go through the origin, but if they're guessing it's proportional and it looks good with it through the origin, I think that's pretty good. All right, I got a couple points above the trend line. I got a couple points below the trend line. This is splitting it pretty darn well. I think that's a good enough trend line for this. So, okay, okay, don't do that again. Okay, let's do the thing now. We want to determine A. Okay, so remember how this works, by the way. We're linearizing because we love a straight line, because we love a slope. And whenever they linearize, we're hopefully feeling pretty good about this at this point. Think y equals mx plus b. What did we plot on y? Well, we plotted the period. What did we plot on x? Well, we plotted 1 over v. What's left over? Because that's the slope. What's left over is a. Right, so they set it up this way on purpose. So be thinking y equals mx plus b. My thing on y is the period. My thing on x is 1 over v. So this must be the slope. And, you know, we're assuming b is 0 if things are working well and our prediction is right. Yeah, so the slope, the A thing they're asking me about is they're just saying find the slope of this line. Okay, remember how to find the slope of a line that you draw, or any slope of any line. You got to pick 2 points that are far away. Pick 2 points as far away as possible. If you pick a point like here and here, number one, if you're off by just like a little tiny bit, it's a hugely different slope. And number two, they're not going to give you all the points because that's a bad method for finding slope, and you know better. So pick 2 points really far away. I did go through the origin, and I'm lazy, so I'm just going to pick the origin. And then let's find a point way over here where it goes pretty well through 2 points. I mean, yeah, this goes over here pretty well too. So my first point is 0, 0. My second point, read your axes really carefully. Every time you're reading a graph, by the way, pay attention to the units because they're going to do kilo, mega, all that stuff pretty often. And pay attention to like divisions. Because like on Y, these are what, going up by 0.05s. And on X, these are going up by 0.01s. So this looks to me like this is going to be 0.4. And this is right on the line here, so that's 1.6. So this point is 0.4, 1.6. Okay. All right. Nice and easy then. Let's find the slope. They're going to see the work on the graph because the graph is like in a box here, so I don't have to really redo stuff. I'm going to rewrite the points I'm using just to be safe. Right, so like the examiner sees my work, but they should see it in the graph anyway. 0.4, 1.6. Okay, and then all I got to do is show I'm taking the slope of the line. So let's make sure we're showing that we're taking the slope by doing y2 minus y1 over x2 minus x1. And 16 over 4 is 4. I think I can keep... Put a decimal place there. 2 sig figs is always honestly pretty safe. A little arguable here. But these smaller divisions go to like 0.25s and stuff, so I think that's fair. All right, so I'm going to say 4.0. I know they're going to say state the units down here, so I don't really have to worry about the units, but I should do it anyway. So it's like, okay, this is this many seconds over this many kilovolts to the -1. So that's like seconds per kilovolt minus 1, which is 4 seconds kilovolts. All right, since I'm looking ahead and I know that that's the next question, so they probably don't need me to do this for this. but I should be in the habit of doing this anyway. Okay, let's see. How did we do? Yes, incredible. Look at this. We picked the points. Yeah, okay. Of course, you don't have to be exact. So they say they'll accept answers anywhere in the range 3.8 to 4.2. So you have a little wiggle room, just not a lot. So, again, draw that line real carefully. So they're looking for, you only get like 1 point for doing the actual math. They're looking for a best fit line drawn through the entire range of the data. They're looking for a large triangle greater than half a line or 2 data points on the line greater than half a line apart. So that's them saying do the slope with 2 lines that are far apart, like at least half the line apart. Okay. All right, state the units of A. We already did that. It was like seconds times kilovolts. Yes. That's it. That's a point. Again, that's a point. This point is worth, the same as any multiple choice question. Get those points. The theoretical relationship assumes that the ball is only affected by the electric force. Suggest why, in order to test the relationship, the length of the string should be much greater than the distance between the plates. This is pretty tricky. And this would maybe not be a first pass question if it's not immediately obvious what the heck they're talking about here. The end of the questions are usually going to be some, tough-ish conceptual thing. This is going to be about if the string was really short and your thing's going back and forth. Well, when it's way over here and way over here, you have a lot of tension force. The tension is like this way, right? There's a pretty significant part of that that's this way. And when you're over here, there's a pretty significant part of it that's this way. And you want the ball to only be affected by the electric force, not being pulled left and right by tension. So a really long string would do that, right? Where you'd have much, much, much less tension pulling you side to side if it's really, really long. That's what they want you to get at. That's probably, maybe not going to be obvious right away. So don't spend a lot of time sweating it. That's 2 points. How many did we get already? Save those 2 points for your second pass, but here's some stuff you could say. Okay, let's jump to number 2 though, because now I got more data, new experiment, and I'm going to have some other, hopefully easy-ish stuff where I can find some points that are easy-ish to get. Okay, so a group of students investigate the bending of a plastic ruler. We got a little scale pan. We put different weights in the scale pan, and it pulls the ruler down more and more and more. So the group obtains the following repeated readings for D for one value of W. They're taking multiple trials like good students and good scientists, because that's what we do. Group divides into 2 subgroups, A and B, to analyze the data. Group A and Group B come up with different mean values. This is fun. Discuss the values that the groups have quoted. They want you to talk about these and explain what's going on with them. And what's implied here is why do they have different means if they took means of the same data? This is definitely a higher level question that they're starting off with. Again, if it's not super obvious, you might come back to this later. Although one thing should hopefully ring a bell for you and make you go, Group A, you're doing one weird thing that I don't like, which is you have too many sig figs. These are all 2 sig figs. There's no way they know the mean to this level of precision. Yeah. So they decided to present their mean with 3 significant figures, even though they got no business talking about this decimal place. Yeah, so that would be one thing to talk about. The other thing is why are they different? And you could, ponder this for a little bit. Why do they get different values? You could even try to play around. This is definitely going to be the number I'm thinking if you average all of this stuff together. How would you get a slightly lower average? Well, what would you do looking at this data? Anything stick out to you? What it's going to be is you have a point that you could reasonably say as an outlier in this 3.6, right? 2.7, 2.9, 2.8, 2.9, 2.7. You might be able to justify saying this is an outlier, especially in IB land where you don't have to say much to justify. So that's the other thing you'd want to identify. So I think that's what they say here. So you get a point if you call out that 3 significant figures is inappropriate for Group A. How dare you, Group A? And rejects trial 3. So if you can say, and Group B, it seems like they called this an outlier, so they dropped that data point. Okay, so again, that's like a tougher one. That takes some thinking off the bat here. So again, like if one of those things sticks out to you, great. If both of them stick out to you, amazing. If none of them do, put a star next to it and do it later. Because here's one that's a little more normal that we might be used to. Zooming out a little bit. They give me a graph. The variation of d with w is shown. So as you put more and more weight on there, it bends the ruler more and more. Makes sense. Outline 1, experimental reason why the graph does not go through the origin. This means I got to talk about what's physically going on. I'm not just talking about math. I'm not just talking about the graph. Why does the graph not go through the origin? Well, I know the one like experiment thing I definitely know is that this is showing some kind of systematic error if we're assuming that it should go through the origin. Remember, systematic error is the error that makes all of your data points like too big or too small. It shifts them all in the same direction. Systematic error shows up as like a intercept almost always. All right, so there's some kind of systematic error, and I want to be like, why? Why, when the weight is 0, is the ruler still deflected a little bit? I want to be thinking about what those variables mean for the experiment. I'm going to come back up to my picture and noodle on this and be like, why? If I have no weight here, why is the ruler still deflected? There's a few things you could say, but we might mention there's systematic error because of, what do you think? I would say because of the weight of the pan. You got this pan here. If there's no weight in it, there's still something hanging from the ruler. So we could say something about systematic error from the weight of the pan. So if we do any kind of specifying a systematic error in the distance, that's what they're looking for. Yeah, and the beam itself or the ruler itself has its own like weight, so you could say that too. Okay. All right, we got some other crazy thing where we're looking at units, and I'm also just paging around because number 2, this is like probably how it's going to go. They get a little harder as you go, so the first parts are definitely easier. This is like going to look pretty intimidating of like, oh boy, there's a theory equation where there's like 2 unknown exponents, and they want to figure out what those exponents are. What the heck? I might put a star next to that and come back because I see down here some more stuff. Suggest an appropriate instrument for taking a measurement and calculate a percent uncertainty. Huzzah! Calculate uncertainty. I love doing that. I'm going to get those 2 points. Right? So again, tackle the stuff that you can tackle. Between number 2 and the end of number 1, there might be 5 or more marks that you don't feel confident about right away. But if you feel confident about like 10 to 15 of these marks right off the bat, that's really, really great. Okay, but let's go through these. Here's what you would do. The hint here is that they're giving me fundamental units. The fundamental units of I are m to the 4th, whatever the heck that is, it doesn't matter. And those of E are this. So I have the units of E, the units of I. They wanted me to pick powers for X and Y that would make this like work. Well, okay. The thing is, I know what W and L are. W is the weight. And so they told me all this unit stuff, so why don't I think about the units? Weight is a thing you measure in newtons, which is a kilogram meter per second squared. And length is a thing that's, it's length. It's a thing you measure in meters. So I think the game is going to be, can I just like make the units balance? So I would go, okay, the units of D. I want to be like, the units of D is also a meters thing, right? Yeah, just making sure L is length and D is also a distance. Okay, so the units of D are meters. And then I'm going to be like, okay, this should work out, I think. It's a little weird because we might have a constant here, but let's try it this way. Okay, the weights is a thing in newtons. So kilograms, meters per second squared. And what do I do? If this was like weight squared or something, I would square it. If it was weight to the 3rd, I would 3rd power it. So we're going to put our X here. And then L is like a meters thing. And I'm going to put my Y here. Okay. E is kilograms, meters minus 1, seconds minus 2. And E is meters to the fourth. Okay. All right, this is tricky. It's a little bit of a puzzle. I'm going to simplify just a little bit because I got two different meters things down here, and those are the ones that are kind of set. So I just, like, you need to pick a power of X and a power of Y that make this all work and, like, give you meters at the end, I think is what we're trying to do here. Okay, the one thing I notice, this is going to be the key to, like, setting this all into place, is you're stuck with 1 kilogram on the bottom. Yeah, like this just is what it is because of whatever the heck E is. So because this is here, I need to cancel this out because I need my units to work out to meters. So X is going to have to be 1. This is just going to have to be first power. Like I can't square it or cube it or anything else because then I have kilograms squared over kilograms or kilograms cubed over kilograms. That doesn't work. So X has to be 1, which means I'm definitely going to have kilograms times meters per second squared. Like that's set. And now it's just what do I raise this meters to make it all work. Let's see what happens now. Kilograms meters cubed, seconds minus 2. Okay, and that's good. I should be using my fraction exponents here, my negative exponents here to make this better. Because I also am catching now that this makes the seconds thing cancel as well, which it has to do that too because I've only got the meters power to play with now, you know? So kilograms has to go away. The seconds to the minus 2 goes away now. And I have like meters over meters cubed times meters to the y. And it's like, okay, meters times meters to the y over meters cubed equals meters. So many meters. So what's the y gotta be? You know, exponent your way through this. I'm thinking I'm going to multiply both sides by m cubed and divide by m. So what do I get? My equals m cubed. So y's got to be 3. I think y's got to be 3 to make that work, right? If this is 3, yeah, then I get meters. Okay, so x equals 1, y equals 3 because I'm just playing like a math game with exponents and units. That one's a lot. That one takes a while. That's a very weird question. That's the best way I got of doing it off the top of my head here. So again, that's like definitely a once even if I start getting here and I'm like, whoa, this is a lot, I'm going to put a star next to it and hope I got time later to come back and spend some more time on it. But I'm going to go find the multiple choice questions that I can do quick before I worry about getting all the way through that. Okay, and before I make my way to the multiple choice, maybe I'll try these. Okay, the ruler has a cross-sectional area, A times B. They're giving me the measurements of A and B in millimeters. Suggest an appropriate measuring instrument for determining B. So I'm looking at B. B is 3 millimeters with a really small uncertainty. So they're just asking if you know like lab equipment stuff. This is a pretty specific one. That you may or may not have used like in your IA and stuff or seen around. But the thing I'm thinking of is a caliper because you want to measure like a fraction of a millimeter. So I'd say a caliper. And I might even say, because this is, I'm noticing the 0.05 thing is a hint that I got like an analog. Well, I guess that's actually them just telling me the size of the thing. But I'm thinking analog because that's like how you know, you're doing half a 0.1 or something. But a caliper would be good to measure. Maybe I could say a caliper that measures fractions of a millimeter, because that's what they're good at. Those are the little pinchy things. So a caliper would be pretty good. Yeah, an instrument capable of reading to that resolution. So we could say a micrometer screw gauge or caliper, a traveling microscope. Okay, that's kind of trivia if you know some equipment stuff. But let's do the last one. The last one is gift. Find the percentage uncertainty in the value of A. A is multiplying. How does uncertainty work when I multiply? Oh, I know how this works. You add up the fractional uncertainties. So I add those up. I add those together. And I should get these numbers, and I should get about 0.05, which is 5%. All right, so the last one, a lot more doable than some of the later questions here. So again, that's the game. Is like, I did these all in order for the sake of the video, but definitely you want to be going through and find, like, of all of those questions, which ones do you think you could get pretty easily? I bet you it's a pretty good amount. Yeah, and if you can pick up those points on the paper 1B early, you're setting yourself up for a good time on your whole paper 1 experience. All right, so go get them. Have fun.